Swayam Prabha. Digital India. Educated India.
Apart from S and T, which are common to the paths, right? So let us just visualize this in a pictorial fashion. So I say that a set of paths from these are 4 internally disjoint paths from S to T, right? They are all vertex disjoint. There are no vertices in common except for the source and the terminus. Fine. For edges, it's a little more tricky. We only demand for edge disjoint paths. Edge disjoint paths, right, means that vertices may repeat. Right? See, for example, you may get a path which looks like this. Right? This is one particular path. You may go from here to here, go to this vertex, take this edge, go to this vertex, take this edge, and then come here. Observe that this top path uses these edges here, and this bottom path uses these edges here. They are all edge disjoint, but they share common vertices, right? So this is edge disjoint, right? But vertices may repeat, right? Here these are vertex disjoint, internally disjoint, right? But if the paths are internally vertex disjoint, they are also edge disjoint. So you see that these two paths don't share, this path and this path do not share an edge in common at all. So vertex disjoint obviously means edge disjoint also. Fine. This is just some terminology. Fine. But what is the main result that we are going to prove? We are going to prove for vertex connectivity, if you have to remove k vertices to disconnect any pair of vertices, say S and T, right, then between S and T there are k vertex disjoint paths, internally vertex disjoint paths. They of course do share S and T. Mengers theorem is actually a stronger statement. I will state the stronger statement. So observe that this is a stronger statement, right? It is not just about 2 vertices, it is about 2 sets A and B. To disconnect A and B, if you have to remove k vertices, then there are k paths which look like this. When I draw it like this, it means that this is the first vertex inside A, no further vertex inside A, no further vertex inside A, and on this path this is the first vertex inside B. Imagine A and B are 2 cities or something like that, right? So you start from a location inside A, right, and you are only interested in talking about the connectivity between the 2 sets A and B. So therefore, when I mean k internally vertex disjoint paths in this case, I claim that there are k paths with the property that the first vertex of each of those paths starts at a vertex of A, no other vertexes from A or B till the last vertex, right. So, this is the first vertex inside B and this is the first vertex, this is the only vertex from A and this is the only vertex from B. I claim that there are k such internally disjoint paths and this is the Mengers theorem. Fine. So, we are going to write a proof of this theorem now. And the reason for writing a proof of this theorem is that inside this proof, you will be able to see the possibility of converting the proof into an algorithm. Right? Otherwise, this statement really does not tell you, right, anything about how to find k vertex disjoint paths, right? None of these things, right? So, given this particular characterization, right, this is what is.
I don't understand the importance of the word internally. What is the difference between internally disjoint and vertex disjoint?
Yes, so when I say two vertex disjoint paths, they don't share any vertices, right? When I say two internally disjoint paths, I mean that they may share one common endpoint. The endpoint, for example, these two paths are internally disjoint. The starting and ending points are one and the same. Right? So, when I say internally disjoint, when I say internally vertex disjoint paths from A to B, I mean that, by the way, it might also be this. Right? So, this additional path that I just drew, right, is also considered to be a path from the set A to the set B, though it starts at the same vertex in A and ends at the same vertex in B. No, it's counted twice. What do you mean by it is counted only once? That path is counted once.
K internally, you said there are K internally disjoint paths, right? So if you are adding one more with the same,
4 becomes 5, right? Alright, now let us do a proof of this theorem. The proof of this theorem is by induction and it is there in the textbook by graph theory textbook by D. Still. Let us do some boundary cases of this theorem, right. So, the first one is A is a subset of the vertex set and B is the whole vertex set. What is this is just becoming familiar with the way problems are approached with respect to this particular problem, right? Because in the statement of the theorem, I said A and B are two arbitrary subsets, right, of the vertex set, right? So, what if A is a subset of the vertex set and B is the whole vertex set itself? What is the vertex connectivity? Number of vertices in A, right? That's because every vertex is a path to itself, just the vertex, right? So, therefore, this is, you must remove all of A, right, to ensure that there is no path from A to B, right, from inside the graph G. If you don't remove a vertex from A, then there is a path from that vertex to itself, right? That path is of length 0, but you want to ensure that there is no such path, right? So, therefore, in this case, the number of vertices to be removed is A, right? And the number of internally disjoint paths is also A. Right? It's a very minor technicality, but I'll just, right? This is actually a very, so look at this, right? Let us look at the path from this vertex to itself, right? So this path is essentially just this. Let's look at this path from this vertex to itself, right? So let us say this is u and this is v. Are they internally disjoint? They are internally disjoint because there are no edges, there are no vertices, the intersection is actually empty. That's why I said it's a technicality, right? You look at the path from u to u, right? Is there any vertex here in between u and u, v? So therefore the number of vertices here, the set is actually the empty set. Look at the path from v to v, right? So the set is the empty set. Are these two paths internally disjoint? Yes, they are disjoint because the intersection of the two empty sets is the empty set. Fine. Therefore, the number of vertices to remove is equal to the number of internally disjoint paths. Fine. It's a technicality, but the first time you have to become familiar with this way of thinking about the paths and reasoning about them. Fine. Really a base case and a boundary case. Fine. So now let us consider the other cases. Right. This boundary case helps us to do a proof by induction on V minus I am going to prove the Mengers theorem, right, by induction on the cardinality of V minus B, right. Is the base case taken care of? The base case is when cardinality of V minus B is equal to 0, that is when B is equal to V, right, and in that case I have already proved the Mengers theorem. Fine. Right. So now let us assume that the theorem is true, right, for all B for which V minus B is smaller than or equal to some number, right. So therefore hypothesis right. So the proof is by induction, like I said. So now we've made the hypothesis. The hypothesis is that the Mengers theorem is true for all A comma B where the cardinality of V minus B is less than or equal to some R, right, for every B. In other words, to visualize this, if somebody shows you an A and B and V minus B is small, right, less than or equal to R, you know that the Mengers theorem is true. What does this mean? If you have to separate the two sets, there are as many internally vertex disjoint paths between those two sets. So much you know for all those B for which V minus B is less than or equal to R. The induction is dependent only on B, right? We don't worry about A at all. Fine. So now I am going to consider a set. Now I am going to prove that the claim is true when for a B where V minus B is larger, R plus 1. Okay. To do this, here is an algorithmic trick. I don't know how to make it work in a certain running time, but it is one. Right? Yeah, sorry. It is, I thought you were protesting. So it is it is a constructive proof, right? And the claim that I am going to prove is that for A comma B, if you have a script P then I'll explain this, right? You can think of this as a rewiring argument. If somebody comes and tells you that, look, I have n internally disjoint paths, right? This is A and this is B. Somebody comes and tells you this, fine. What I am telling you, I am going to prove to you that you can rewire it in such a way that, so let me give names here, A1, A2 to AN, B1, B2 to BN. You can now rewire in some way. Maybe it is A1 to B5, A5 to B1, right? And you will get one more path. After taking care of all the n terminals, so to speak, that is A1 to AN and B1 to BN, you will get a new path, right, which is AN plus 1, BN plus 1. Right? Don't be misled. It is also possible that it may be A1 to BN plus 1 and AN plus 1 to B1 also. That is also possible. So essentially, I will argue that it is possible to, because the number of paths is lesser than the connectivity, you can rewire the roads, right, between the endpoints so that you can introduce two new endpoints. I am going to argue that this is possible by our induction hypothesis. It will follow from our induction hypothesis. Right? So let us assume that it is this statement that is true in our induction hypothesis. Right? So I am just making a small modification to my proof. I made the induction claim earlier. Assume that it is this claim which is true by induction on the cardinality of V minus B. Right? So proof by cardinality of V minus B. Fine. So which means, what do you know? For B for which V minus B is smaller, this rewiring will work. Right? Intuitively, what does this mean? If you have a set A and if you have a large set B, right, and if you have some internally vertex disjoint paths, you can rewire. Right? So now when this B becomes smaller, we want to write the proof. When V becomes smaller, B becomes smaller, V minus B becomes larger, we want to set up the induction. Fine. So now let us just set up the induction in an interesting way. So now what is the starting point? The starting point is there are these n internally vertex disjoint paths. Right? So now what do? You simply take an arbitrary path called R that goes from A to B. Take any path, goes like this, right? So case 1. So this one is called R, okay? Case 1. This path R is internally disjoint from paths in P. You are done. Right? What is my claim? My claim is that I can take this P1, P2 to Pn, this set called P, right? Take P union R. That is a proof of our claim. I am claiming that you will find one path which introduces, right, which is one more path from A to B, right, which does not share any vertex of the set of paths P. This is what I am claiming, right? Then we are done, right? So case 2. So therefore now you should think from an algorithmic point of view, what will you do? You just have to pick a path from A to B, right? And then you have to check if it is disjoint from all the paths P1 to Pn, right, except the endpoints. It may share a common endpoint, I don't care. This is another algorithmic check that you should do. Case 2, right? It turns out that R is not internally disjoint. From all paths in P. Now applying mathematical logic, right? Let Pn be the path that contains So here is a thought experiment, right? Somehow I have to create one more path somehow, right? So what do? I look at R. I look at R and ask, I look at each vertex, right? Is this the last vertex which is common to some path in script P? I keep asking. If the answer is no, I will go to the next vertex which is common to some path in P. This procedure will end finally, right? Because it will end because you know that R is not internally disjoint with all the paths, which means there is a last vertex from R which is common to P, right? So what I hope the thought process is clear, right? In some sense, okay, this picture is not well drawn, so let me erase this part. So the path from R looks like this. This is the last vertex which is common to any path in P, and after that it charts its own new set of vertices it brings and ends inside B. Fine. Let us call this vertex X. Fine. Now what are we going to do? We are going to look at the proof is almost done. I need about 5 minutes, right? And to set up the whole induction. Now what am I going to do? I am going to look at this X is on one path, right? See, X is common to some path, right? That X can occur only in one path inside P. Let me pick that particular path and let that path be Pn, just for it doesn't matter, it might be, I just call it Pn. Fine. Now let me get rid of the index n and let me call that P. Now I am going to focus and say that let us consider the part of P that starts from X and ends at P, ends in B, and let me look at the part of R that starts at X and ends at B. Observe that this is a rewiring argument. We are going to cleverly use induction and get one more internally disjoint path somehow by magic now, right, by applying the induction, right. So, to set up the induction, I choose a superset of B. How am I going to choose a superset of B? I am going to look at X. X is sitting on one path. After X on R, nothing is on any path in P, right. So, that part is called XR. That is, all those vertices starting from X and on R, that is completely disjoint from P by choice. On P, from X up to B, there is this particular path. So, I consider the vertices of X are I am designing the B so that I can apply the induction hypothesis now. And this is a step of, this is a very nice clever step to apply use the induction, right. I hope the choice of B's, right. Consider B prime, right. This vertex is called X, okay, and X is here. Consider B prime to be this one, okay, I am out of time, right. Right. Now, I will show the induction conclusion and I will stop, and then when we meet later in the day I will complete the proof. Fine. Apply induction, apply the induction hypothesis on A comma B prime, right. So, B prime is a strict superset of B because B prime contains X, which is a vertex which was neither in A nor in B, it was inside that particular. So, it is a strict superset. So, it is not, the cardinality of B prime is not, right, cannot be equal to the cardinality of B, it has one more vertex. So, therefore, V minus B prime is less than V minus B, right, and therefore I can apply the induction hypothesis, right. I will continue from this slide when we meet. Yeah, thank you.